Merci, donc c'est un plaisir pour moi d'introduire la conférence de Manjul Bhargava aujourd'hui. Je crois que c'est pas la peine de parler trop longuement du conférencier, j'en dirai quand même quelques mots. Manjul est né en 1974 à Toronto. Ses parents avaient émigré quelques années auparavant en Inde et ils se sont très vite installés aux États-Unis, où Manjul a suivi l'ensemble de ses études et a fait sa carrière scientifique. Je ne vous étonnerai pas en disant qu'il a montré très tôt de grands dons pour les mathématiques. Il a d'ailleurs été formé en mathématiques par sa mère, qui est professeure dans cette discipline. Il a eu une scolarité brillante et en 1992, il a été reçu à l'université de Harvard. Il a passé 4 ans avant d'aller à Princeton, où il a préparé et soutenu sa thèse, son PhD, sa thèse, sous la direction d'Andrew Wiles, qui est célèbre pour avoir démontré le théorème de Fermat, une conjecture par Pierre de Fermat qui avait résisté pendant plus de 3 siècles aux efforts des plus grands mathématiciens. C'est donc dans la théorie des nombres que Manjul s'est illustré. Il a établi un certain nombre de résultats dans cette théorie qui lui ont valu en 1974 la médaille Fields de mathématiques. Il avait avant cela été nommé à l'âge de 28 ans professeur à l'université de Princeton. Mais je pense qu'il est difficile de résumer la carrière de Manjul en parlant que de ses talents de mathématicien. Il est également connu pour ses dons artistiques, pour son intérêt pour la musique. Il joue lui-même un instrument de musique traditionnelle indienne, pour son goût pour la poésie sanscrite et pour en général son goût pour les arts et l'histoire de l'Inde. C'est d'ailleurs en Inde que j'ai eu le plaisir de le rencontrer pour la première fois il y a quelques semaines, dans une conférence où il nous a déjà parlé précisément du mathématicien Ramanujan. J'ai dit qu'il était spécialiste de la théorie des nombres et je pense que c'est vraiment le domaine des mathématiques qui fascine le plus même ceux qui n'ont aucune connaissance en maths. C'est un domaine qui est très particulier et paradoxal puisqu'il concerne les concepts les plus intuitifs que l'on peut avoir en mathématiques, c'est les nombres entiers. Les énoncés sont extrêmement simples. Le théorème de Fermat s'énonce de façon immédiate, mais malgré cette simplicité, la démonstration des résultats est extrêmement complexe et fait appel aux concepts mathématiques les plus sophistiqués, en particulier celle des courbes des fonctions elliptiques dans lesquelles Manjul s'est illustré. Et le mathématicien dont il va nous parler, Ramanujan, était un génie ou un virtuose des nombres. Il a autodidacte, il s'est formé tout seul, il a retrouvé un très grand nombre des résultats des mathématiques du XVIIIe et XIXe siècle, et il a énoncé de façon complètement intuitive des conjectures mathématiques dont certaines résistent aux mathématiciens jusqu'à maintenant. Il n'a pas été seulement un mathématicien exceptionnel, il a eu également une vie extrêmement intéressante, très romantique, et romanesque je dirais, ce qui explique qu'un film a été tourné sur sa vie dont Manjul va nous parler. Donc c'est en fait l'exposé que vous allez voir aujourd'hui, c'est l'exposé sur un grand mathématicien indien, par un grand mathématicien indien, et je pense que nous avons vraiment le privilège d'assister à une conférence exceptionnelle aujourd'hui. Et je laisse la parole à Manjul, and we will shift from French to English now, I think. Manjul, from yours.
Bonjour and namaskar. I'm sorry, my French is not quite good enough to give a lecture in it. So sorry for switching to English. Also, one of the things I want to talk about today, where's this noise coming from? One of the things I want to talk about today, in addition to the gems of Ramanujan and their lasting impact on mathematics, I want to talk a little bit about the film that is going to be coming out about Ramanujan called The Man Who Knew Infinity. So before I start, I want to thank UNESCO for the idea for this conference that's starting now and will be going on tomorrow. I'm very grateful to UNESCO for this idea, particularly to Ambassador Rujaya Kaboji, whose idea and whose work has led to this conference. I also want to thank to New Delhi, and as I say, for all their work in arranging the lecture here in Jusio. So what I'll be talking about are the gems of Ramanujan and their lasting impact on mathematics. Ramanujan is a mathematician who I grew up learning about, being from an Indian family and being interested in mathematics. This is a mathematician that I really grew up learning about and admiring and being inspired by. And so I grew up learning about him. And then when I was later on a student, a book about Ramanujan came out called The Man Who Knew Infinity, written by Robert Canigal. So that's a picture of Robert Canigal there. And the book on the left there is the cover of the biography written by Robert Canigal about Ramanujan, The Man Who Knew Infinity. And if you haven't read this book, I highly recommend it. It was a New York Times bestseller in the non-fiction category, and it was a real eye-opening book for me personally, and for many young mathematicians who started reading this book and started getting excited about mathematics. It's an unusual biography in that not only is it a story about his life, but it also describes, in a not trivial way, some of the mathematics that Ramanujan did, and the kinds of things, kind of really different kind of mathematics that he did that really inspired so many people when they started to learn about his mathematics. So already at that time, with being inspired by this book and seeing the amazing story of Ramanujan, already at that time I thought, wouldn't it be amazing if this book could be made a movie? And I was already thinking that at that time, and all the years went by, and over the last 10 years, there's been talk about a possibility of a movie being made about this book, and I've been involved with this for 10 years, and finally, this dream come true. A book based on Robert Canigal's biography of Ramanujan. Also, the movie will be called The Man Who Knew Infinity. It stars Dev Patel from Slumdog Millionaire as the lead, playing Ramanujan. And that's a picture of Dev Patel playing Ramanujan. So, let me tell you a little bit about Ramanujan's life. So, he was born in 1887 in a town called Pallipalem. And he grew up in Kumbakonam, in Tamil Nadu, which is a state in southern India. And one thing to note, so even though he didn't, I'm going to say in a little bit, he didn't really have that much of an education, a formal education in mathematics. But it's interesting to note that his home was always filled with Carnatic classical music, the classical music of southern India. And so he grew up with this kind of music in his home, which was a big inspiration to him, even mathematically, classical music being a very mathematical kind of music. And so even though he didn't himself pursue music, that music was certainly a part of his upbringing. So Ramanujan was an outstanding student growing up, not surprisingly. He won many academic awards and earned his scholarship to college. But his mathematics level was way beyond what he was learning in college, and most of his mathematical explorations he was doing on his own. And he was very, very good at this. For example, he discovered much of trigonometry all by himself at the age of 13. And then when trigonometry came up in school, he was a little disappointed to know that it had already been done before. That happened to him a number of times in his life. And he would discover entire fields of mathematics only to find out that those were known before. As he discovered more and more things, mathematics really started to become a passion for him. And he didn't have, as I said, that much formal education in mathematics, but he did find a certain book. And all it takes is one book for that inspiration to happen. And for him, this book was a book by Carr, C-A-R-R, called Synopsis of Elementary Results in Pure Mathematics. And as he read through this book, it really ignited his passion for mathematics. And here's Hardy's description of this book. It's this book that inspired Ramanujan contained enunciations of about 6,000 theorems, systematically and scientifically arranged, with proofs, which were often little more than cross-references. So it had 6,000 theorems. Not really much of proofs, it was just a collection of theorems, and this was the book that was used in Cambridge to study for the examinations. So it was just a collection of theorems that you were supposed to know, but it didn't really have explanations in the usual way that mathematicians would write. Well, if you have 6,000 theorems, there's not much room for explanations. So this was Ramanujan's inspiration. He went and understood those theorems by himself, in his own way. And then following the style of this book that inspired him, he recorded his findings in notebooks as well, in a very similar style, theorem after theorem, that he would come up with, he would write down and collect them. Pages and pages worth of these theorems. So this pastime of writing theorems in the notebook and collecting more and more of his mathematical visions became his obsession. He started to spend all his time on mathematics. And while he used to be a very good student, once this happened, he flunked out of college. Twice. Because he was spending all his time on mathematics. It became a real obsession for him. And he spent many hours in his temple lobby, his local hometown temple. He spent time in the lobby listening to drums. Remember that background that he had in Carnatic classical music? He was hearing that also in his temple. The tabla drums, which are the classical drums of South India. He would listen to them sitting in the temple lobby, and that would be his inspiration to write more and more mathematics. And this was all coming completely without a source of education. It was coming entirely from his own creation, just inspired by that one book. He also worked on mathematics a lot in his home, where 6 people lived in one room. He didn't grow up in a very well-to-do family. In fact, his family was very, very poor. And now, this is kind of an inspirational. I found this inspirational when I read about this, because when we go and work, it often happens that people, when they get an office, they complain, "Oh, this isn't big enough," or "I have to share it with somebody." Here he was working with 6 people in one room and doing just amazing amounts of mathematics, decades worth. What one person would normally do in decades, he was doing in months, in a room filled with 6 people, one room, where he lived and worked, and where others lived and worked. To help alleviate the poverty that his family was facing, he found a job doing clerical work. And so he was basically a clerk for a long time, and in free hours after his job, he would work on his passion, mathematics. So all free hours outside his clerical job were spent doing mathematics. So that was great. The only problem was that no one in the area could understand a thing that he was writing or saying. So much so that lots of people thought he was kind of crazy. You'd look at what he's writing and it would make no sense to anyone. And nobody really had an idea of what he was writing was correct, or whether it was just a crazy person writing random symbols on a page. And how could you really tell the difference if math wasn't your thing? And even the local mathematicians for whom math was their thing, they couldn't comprehend what Ramanujan was writing down. But he did have support, great support from his family. They encouraged him to do mathematics. They wanted to understand what he was doing, what was inspiring him. He had an arranged marriage, and when his wife came, his wife also wanted to really know, what are you doing all day long? And there's a scene in the movie that describes one of the first times that he meets his wife, and his wife wants to know. His wife was one of his greatest supporters throughout his life, and so maybe I'll show you a scene from the movie where Ramanujan tries to explain what he's doing all the time to his wife. I'm wondering if we should move that curtain a little bit up so that it's a little bit darker, so you can see a little better. So one thing that Ramanujan always said, and what pure mathematicians always say, is that to mathematicians, mathematics is an art. It's a creative, it's a flow of creativity. And it's a search for beautiful patterns. And this is what Ramanujan always used to try to explain to those who didn't understand exactly what he was doing. And so this is Ramanujan meeting his wife, and his wife being perplexed and him trying to, so this is in the movie. We try to tell the public, the director and writer does a wonderful job in expressing the joy that mathematicians feel when they're doing mathematics, that creative spirit, that flow of creativity, that beauty of patterns that mathematicians feel when they do their mathematics. We don't normally see that in school, but for research mathematicians, that's what mathematics is like. And that really hasn't been portrayed in film before. Usually when mathematicians and scientists are portrayed in film, they're usually a crazy kind of person, antisocial, and you never really get to see them as artists, which is how they really feel that they are, and as normal social human beings. So this movie really changes that, and so that's why we're very excited. If this movie does well, that may encourage more such movies in the future where scientists are actually portrayed as human beings. Okay. Well, it would be nice if there was sound.
Go ahead. You can look. Please.
What does it all do?
It's like a painting, I think. Only imagine it is with colors you cannot see.
What good is that?
Not much for you, I'm afraid. But for me, it is everything. Maybe there is someone else who can see and understand it as well. And for them, it will be important.
Have you met them?
No, not yet.
I want to understand. More than just colors I can't see.
What do you see?
Sand?
Yes. Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything. The color in light, the reflections on water. In math, these patterns reveal themselves in the most incredible form.
So that's Ramanujan explaining the way he thinks about mathematics during one of his first meetings with his wife. So his family was very supportive. They wanted to understand how he thinks and what inspires him. And they were very supportive, even though nobody around could actually understand the mathematics that he was doing. And this was very difficult for him because he was writing pages every day of new mathematics, and people couldn't understand what he was doing. And so he was encouraged by friends and family to write to mathematicians outside his hometown. And well, he wrote to many mathematicians around the world, sending him samples of the theorems that he had come up with. And of course, most people would look at his mathematics, not understand a word, and think it was a crank, and throw it straight in the dustbin. And that could have just happened forever, and we'd never know the mathematics that he did. But luckily, he also wrote to a mathematician named G.H. Hardy, who was considered to be, well, perhaps, if not the greatest mathematician of that time in particular area of number theory. And so he wrote a letter to G.H. Hardy. And we know what he wrote in there. He wrote in beautiful English, in beautiful handwriting. And he sent many, many pages of mathematics with a cover letter. And here's a sample of some of the things he said in the cover letter. He says, "I beg to introduce myself to you as a clerk." So you can imagine that first sentence was enough for many people to just throw the letter straight in the garbage. "I beg to introduce myself to you as a clerk. I have had no university education." Okay, if they got past that first sentence, they certainly weren't going to read after this. "I have not trodden through the conventional regular course, but I am striking out a new path for myself. And the results I get are termed by local mathematicians as startling." So it's real credit to Professor Hardy, who is at Cambridge University, Trinity College in Cambridge, that he read this far and decided to look at some of the mathematics that Ramanujan actually wrote. And there were some others who did get past this point. So this is a picture of Hardy on the left there. And Hardy is played by Academy Award winner, the legendary Jeremy Irons. And as you can see, the resemblance is quite amazing. And he does an absolutely amazing job as Hardy, as I'll show you in a second. So let me tell you a bit about what was in the letter. So here's something Ramanujan wrote in his letters that made people think he might be a bit crazy. He had the following equation. It's one of the first equations that he writes in his letter. So if people even got this far in the letter, at this point it was clear they should throw it in the garbage for most people. So he says that 1 plus 2 plus 3 plus 4 plus all the way up to infinity is equal to minus 1/12. What on earth could that mean? Most people thought that was just some crazy sentence. But Hardy recognized this immediately as a theory of what's called analytic continuation in complex analysis. And if you've ever done complex analysis, then this is actually something that naturally comes up in the theory of analytic continuation of the Riemann zeta function. And so this actually does have a meaning. Now, Ramanujan never had any course in complex analysis. How on earth did he come up with this? He had some completely different way of thinking that led to this equation that most people would think make no sense. But in the theory of complex analysis, it does make sense, and Ramanujan arrived at it without having taken any course in complex analysis. The fact that Hardy thought this wasn't an unreasonable thing to say, and that he knew where it was coming from, that was an indication that Ramanujan had perhaps finally found someone who understood him. So that was one thing that Hardy didn't think, okay, this is a prank. He was willing to go further into the letter. And as he went further into the letter, there were things that were just completely out of this world that he'd never seen before. And to tell you about one of the... Wow. Out of this world, okay. So I want to tell you about one of the first things that Ramanujan wrote. Mathematical thing that he wrote. So to tell you about it, I want to tell you one kind of really beautiful mathematical tidbit that to mathematicians is standard. So here's a basic question in mathematics, which is, what is the value of x equals 1 divided by 1 plus 1 divided by 1 plus 1 divided by 1 plus forever? Turns out that, so what does that mean? That just means that you take it 5 steps, you see what you get. You take it 6 steps, you see what you get. You take it 7 steps, you see what you get. And you take that sequence of numbers that you get, and does it approach a limit? So that's what it means to say this, that 1 over 1 plus 1 over 1 plus 1 over 1 plus dot 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 forever. It's what it approaches as you take n steps for bigger and bigger n. Okay, so what is the value of that? Turns out it does have a value. In other words, it does approach a limit as you take more and more steps. And here's how you evaluate what x is. What you note is that x is equal to 1 over 1 plus x. Now why is that? Well, the point is, I'm going to turn some of that, so that if you look at that big expression for x, I'm going to turn some of it red. Okay, and if you look at that right portion of that expression for x, what is that? It's the same expression. That's x. So that expression for x contains a copy of x right inside there. So why not just put x there? And that gives the fact that x is equal to 1 plus x. And now we can solve for x. Right? So if you multiply both sides by 1 plus x, and then subtract 1 from both sides, you get that x squared plus x minus 1 is equal to 0. And so in order to figure out what that expression x was, you just have to solve this quadratic equation in x, which by the quadratic formula tells you that x is equal to minus 1 plus the square root of 5 divided by 2. And so that's a standard thing for mathematicians, that you can evaluate infinite, these are called continued fractions, infinite continued fractions you can evaluate by tricks of that kind. This number is called the golden ratio, by the way. So this is a famous expression that mathematicians often use for the golden ratio that comes up everywhere in nature and art. But this is a very artistic way in mathematics that the golden ratio comes up. It's just this beautiful expression, infinite expression. Okay, so this is standard to mathematicians. Ramanujan really enjoyed continued fractions, and he defined the following continued fraction. He said, let's define r of q to be the same continued fraction, except in the numerators, we'll replace the numerators, instead of going 1, 1, 1, 1, 1 with the numerators, we'll make them 1, q, q squared, q cubed, and so on. So what is r of q? Now, how do you evaluate that? Well, the same trick doesn't work, because there's no smaller part that looks exactly like it now, because the numerators are changing as you're going down. We do know that if you let q equals 1, then the numerators are the same going down. And that's the case that we already did, where we got the golden ratio. So r of 1 is equal to minus 1 plus square root of 5 over 2, the golden ratio. That we know. But can we evaluate this for any other values of q? That was Ramanujan's question. And the letter. And the first example he gave, he said that I can evaluate this for other values of q. And the values that he could evaluate it at, the values of q that he could evaluate it at, were kind of crazy looking. He could evaluate it at e to the minus 2 pi. So e is this number, right, the famous exponential number 2.71828. And then pi is the usual pi, circumference divided by diameter. He took e, he raised it to the minus 2 pi, and he put that into the value of q in that big fraction. And he said he can evaluate that, and it's equal to e to the 2 pi over 5 times this expression, which is kind of similar to the golden ratio. So this is a really beautiful, to mathematicians, this is a kind of equation that mathematicians find really beautiful, because it involves e, which is one of the most fundamental numbers in mathematics, it involves pi, and it involves the golden ratio. They're all there, sitting in one equation, in a way that had never been seen before. And Ramanujan wrote that one down, and then he writes this unbelievable claim. I can actually evaluate r of e to the minus pi square root of n for any positive rational number n. And he said that without any details. He just said, I can do that. And that was one example where he put an e to the minus 2 pi. There's just one example where n is 4. So that was something that was one of the first things in the letter. Now, most mathematicians, when they got to this point, they thought, okay, well, this is how could this possibly be true? No one had any techniques to evaluate a continued fraction of that kind. And usually they threw the letter in the garbage at this point. Hardy's reaction was different. He said, these formulas defeated me completely. So first of all, what made it different for Hardy than other mathematicians is that there were many formulas, well, not many, but there were at least a couple of formulas, non-trivial ones, that Hardy could actually prove. That looking at Ramanujan's letter, he could justify some of the things in there. But then, something like this, he was completely stumped on. But the fact that he was able to verify a couple of the claims, and then go on a little bit further and be completely defeated, he felt that there must be something going on there. So he says, these formulas defeated me completely. I had never seen anything in the least like it before. They could only be written down by a mathematician of the highest class. And they must be true, because no one would have the imagination to invent them. How could you come up with something like that if it wasn't true? So he did believe that these things must be true, but he thought the chance that an uneducated Indian clerk was coming up with that was a highly unlikely scenario. So one of his first guesses was that maybe he had another very illustrious colleague at Cambridge who also worked in number theory in a similar area to Hardy. They had a lifelong collaboration named John Littlewood. And he thought maybe it was Littlewood they used to play pranks on each other. Maybe this is one of his pranks. And so here they are. Here's Hardy and Littlewood. Littlewood is played by Toby Jones. Wonderful actor, Toby Jones. And here they're playing tennis. And Hardy brings up this prank. He says, I understand what you're up to.
You know, Littlewood, this year alone, I've received correspondence from those who profess to prove the prophetic wisdom of the pyramids, the revelations of the elders of Zion, and the cryptograms which Bacon supposedly buried within the plays of the so-called Shakespeare. But a letter from an ill-educated Indian clerk in Madras challenging assertions I made in the track series really takes the biscuit.
Well, I have to say, I've made similar assertions myself.
So you admit it?
But this was 3 years ago.
No, I'm talking about the letter. Bloody brilliant, I thought. I don't know where you got the postmark. Almost had me fooled.
I simply don't know what you're talking about.
Oh, come on. I'm not a complete idiot.
I don't know how to get this into your thick skull, but whatever it is you're talking about, I'm simply not involved. Play.
So, you've missed home?
Not angry. I tell you, there is a war coming, no doubt about it. Because we are being led like mindless, spineless sheep. No one bothers to question any of it. It's coming all right, you can smell it.
You're as paranoid as Hardy.
With all due respect, Bertie, you couldn't hold a candle. Little, but I have a word.
Yes, of course. Integrals, infinite series, God knows what else. Oh, excuse me. Always forget you don't believe in a supreme being.
All right.
This chap turns out to be genuine, you might have to reconsider.
Well, it must be genuine. Who'd have the imagination to invent all that?
Well, I'm rather flattered you thought I did. These two infinite series are the more intriguing.
Yeah, they're defeating it completely. I've never seen anything like them.
Well, it's deceptive. I'll wager the hypergeometric series.
A great Littlewood stumped. He's hot class, I'd say. Being inexperienced, I would very highly value any advice you give me. Yours truly, S. Ramanujan.
What does the S stand for?
Not himself.
You intend to invite him here?
Oh, no. Much better. Let him rot away in his office in Madras.
So as you can see, he decided to invite Ramanujan to Cambridge, which shocked everyone at Cambridge because he was about to invite somebody without a college education from India during World War I to come and work in Cambridge. So Hardy invited Ramanujan to Cambridge, and they started working together and had one of the most productive collaborations of all time in mathematics. And maybe I'll show you a scene from the movie when Ramanujan has come over to Cambridge. And knowing that Ramanujan has had very little education, In particular, he's never gone through the formal methods of proof that the mathematicians would normally use. He wanted him to take some classes to learn the formal methods of proof, even though Ramanujan had proven hundreds, almost maybe thousands of theorems at that point. At least in his head, not written out. But written out the theorems, but not the proofs. So this is one of the things that tension in the movie is the way that Ramanujan thought about mathematics was very different than the way that everybody else did, because he had never been brainwashed by the usual education system, which hardly needed in order to publish papers together.
Ramanujan, we decided that for the good of everybody, you should attend some lectures.
But I'm here to publish.
Yes, one of a time, I hope. But first we need proofs of your work.
It's really nothing to worry about. It's simply a question acquainting you with the more formal methods that will benefit our future work together.
I mean, we need a common language. You wouldn't expect us to converse with you in town.
No. But you expect me to speak English.
Quite. So, there'll be plenty of time to publish.
Sorry, but with all humility, how does anyone know that? I don't want this to lie with me.
I'm sure you will work.
Thank you, sir. But I have much more to share with you. As I told you, the letter only contained a small sampling of my discoveries. You'll see, I have even found a function which exactly represents the number of prime numbers less than x in the form of an infinite series.
Exactly.
Yes, I thought if we were going to publish, it should be something groundbreaking.
This is most unexpected.
Buddy, this will take a lifetime.
Maybe two.
But it was a real struggle for Ramanujan. For one thing, while he left home, he had to overcome severe racism. There were very few Indians invited to Cambridge at that time, especially ones who had he was the only one who had no college education. World War I was going on at the time, so he was there, coming from colonial India during World War I. And besides the racism, the biggest hardship for him was finding food. English food, as many people can relate to, was very difficult for him to eat. But especially because he was vegetarian, and the notion of vegetarianism was unheard of in England at the time. And so getting vegetarian food was extremely difficult, and so he would often just not eat for days, and would be working with severe malnutrition. But despite these hardships, for his field-changing work that he did just in that span of 5 years that he was there in Cambridge, he was elected Fellow of the Royal Society, which was, of course, one of the greatest honors that a mathematician could get at that time. But unfortunately, the malnutrition really had an effect on him. It lowered his immunity so much. He was also not used to the cold weather, coming from Madras. And so due to these factors, he fell very ill. He returned home as soon as the war ended, where he died 1 year later, in 1920, at the age of 32. Even on his deathbed, that last year in Madras that he spent, which was on his deathbed, he finally had a reunion with his wife, who was not able to come to England because of the World War that was going on at the time. Even on his deathbed, when he got home to Madras after the war, he continued to produce just absolutely incredible mathematics, being incredibly ill, but producing incredible mathematics. And some of that mathematics is continuing to transform the field, not just in mathematics, but also in physics and neighboring areas. And many things that he wrote in that last year, and in the notebooks that we've found since of his, we're still trying to understand today. And it often happens that when we understand something further from his notebooks, it completely transforms the area that he was writing about. And that still continues to happen. This tension that existed between Hardy and Ramanujan, that took them a while to really get going. The fact that Hardy wanted proofs from him, and Ramanujan was just writing theorem after theorem, one after another, not wanting to waste time on these proofs. That is, of course, one of the major themes of the movie, and how they overcame that obstacle. And here's one scene where Hardy's really trying to explain why this is important, and why Ramanujan really should try to make others understand what he's doing in the way that he does.
How do you know that theorem?
It came to me. Mr. Hardy, I don't understand why we waste our time doing all these proofs. I have the formulas.
It's not that I can't see what you've claimed. It's that I'm not sure that you know how you got there. Or indeed that your claims are correct. There are subtleties which...
But they are right, sir. I have more important new ideas.
Yes, but intuition is not enough. It has to be held accountable. And a little humility would go a long way. Why do you think they want us to fail?
Because I'm Indian.
Well, yeah, there is that. But also, because of what we represent. Now, Euler and Jacobi, who were they?
Mathematicians.
Just names to you. Euler was the most productive mathematician of the 18th century. Most of his work done after he was blind. Jacobi, like you, was snapped from obscurity and was almost as impressive as Euler. Now, I think you are in their class. What they had in common, what I see in you, is a love of form. It's all through your notebooks. Let me ask you something. Why do you do it, any of this?
Because I have to. I see it.
Like Euler. Form for its own sake. An art unto itself. And like all art, it reflects truth. It's the only truth I know. It's my church. And you, just as Mozart could hear an entire symphony in his head, you dance with numbers to infinity. But this dance, this art, does little to endear us to certain factions who see us as mere conjurers. So if we are going to challenge areas of mathematics that are so well trod, we cannot afford to be wrong. I need you to attend your lectures, don't offend your professors, and keep doing your proofs. Otherwise this experiment of ours will be doomed to failure. Come with me. I want to show you something. There are many ways to be honoured in life. For us, being elected fellow is certainly one, but in my humble opinion, to leave a legacy here at the Wren after we're gone is the greatest. This library houses the epistles of St. Paul, the poems of Milton, Morgan's Bible. But in my estimation, as a man of numbers and pièce de résistance, is Newton's Principia Mathematica. Now, just as Newton represents the physical aspect of our work, your notebooks represent the abstract. It took a long time for Newton to be proved, which is why we have an obligation to prove these. And if we do, I believe that one day, these notebooks will find their place here. Now, do you understand what's at stake here? Good.
It took some time for Ramanujan to start to write the way Hardy wanted, but once he did, he actually came up with some incredible proofs. And some of those proofs, too, the techniques behind them have transformed areas of mathematics. And I'll explain that in a little bit. Mathematicians often wonder, it took Ramanujan so long to get started, and once he was started, he did so much in just that span of 2 or 3 years. And one wonders, we're still trying to understand some of the things that he wrote down, and one always wonders if his wife had been able to come, if he'd been able to get vegetarian food, or if he'd been able to travel home, if the World War wasn't going on, and basically if he had been able to live beyond the age of 32, how much mathematics would be different today. Already with just those 3 years of work, mathematics completely changed. So what can we learn from Ramanujan? There are two answers, I think. One is, first of all, his mathematical legacy. His ideas, of course, have inspired and continue to inspire generations of mathematicians. A lot of the great accomplishments of the 20th century have involved ideas that came from Ramanujan's notebooks and works. So, for example, the proof of the wave conjecture is due to Deligne. Monstrous moonshine and the proof of Fermat's last theorem also involve ideas of Ramanujan, which led to, as you can see, Fields Medals for Deligne in 1978, Portraits in 1998, and the Abel Prize for Andrew Wiles this year. That work also involved ideas of Ramanujan. So Ramanujan's mathematical legacy is, of course, huge. But almost more than that, I think what Ramanujan's story tells us is a broader legacy, which is that talent can really be found anywhere, even in the most unexpected, most uncompromising places, regardless of background or economic status. And so it's really our duty as a society to find talent and nurture it. And the way to do that is really to make sure that education is available to every child in the world, so that we can find those people and find those talents and nurture them. And that's very important for the progress of society and for the well-being of people. So this, I believe, is really their even bigger legacy than Ramanujan's mathematics, is that really it's possible, it easily could have happened that that letter to Hardy wasn't discovered, and his immense amount of talent would just be unknown to the world forever. And I was just very lucky, but there may be many such Ramanujans in the world who we've missed over the years, and we have to do everything we can to make sure that we don't miss them, not just in mathematics, but in every area. Okay, so I want to just tell you, the movie, of course, I'm very honored to have been an associate producer on that, on The Man Who Knew Infinity, and I'm grateful to IFC Films for giving us those clips before the movie's released. So these clips are not available anywhere; they're just privately given by IFC Films, who's the distributor of the movie. And I'm very grateful to the director and writer who inserted quite a bit of mathematics, more mathematics than you typically see in a Hollywood film. But of course, there are lots of mathematical gems of Ramanujan that couldn't be in the movie, and that's what I wanted to tell you a little bit about before I wrap up. So here are just a sampling of the kinds of mathematics that Ramanujan did that are fairly accessible to the general public. So one thing that does come up in the movie is the notion of partitions. So what is a partition? We say that P of 4 is equal to 5, okay? Since we can partition 4 in exactly 5 ways. So what does that mean? Well, if you take the number 4, you can write it as 4, you can write it as 3 plus 1, you can write it as 2 plus 2, 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. There are 5 ways that you can break up 4 as a sum of smaller numbers, right? So everyone see that? There are 5 ways that you can break up 4. So P of 4, we say, is equal to 5. Similarly, P of 1 is equal to 1, right? Because you can only break up 1 as 1. That's it. P of 2 What is P of 2? 2 you can write as 2, or you can write it as 1 plus 1. So P of 2 is 2. Okay, how about P of 3? 3, 2 plus 1, 1 plus 1 plus 1. Okay. So P of 3 is 3. Okay, and similarly, you can work out P of 8 is 22. P of 16 is 231. Everyone see the pattern? P of 32 is 8349. Okay, I'm just going to show you some powers of 2, so you can see if you see any pattern. Okay, if you don't see a pattern, you're not alone. This was a long time unsolved problem to work out. If you take P of n and you let n go to infinity, how fast does that grow? And when people looked at this function, they weren't sure whether there would even exist if there were doubts. Most mathematicians were starting to think that there really is no formula that tells you how P of n is growing as n goes to infinity. At least no natural formula. And so that was a long time unsolved problem. How does P of n grow as n grows? Okay, what is the function? What is the rate of growth of this function, of P of n as n gets bigger and bigger? So in other words, how does it grow if you take a number n and you break it up into smaller pieces? As that number grows, the number of ways you can break it down, how does that grow? And so that was a long time unsolved problem, often considered impossible. And for the first time in history, Ramanujan came up with an asymptotic formula for P of n. And here it is. P of n grows like 1 over 4n square root of 3 times e to the pi times square root of 2n over 3. Notice all those e's and pi's. No one expected e's and pi's both to occur in the answer to this problem. And so this was a formula that Ramanujan wrote down in one of his letters to Hardy. And where's E? Yeah. So this was one of those examples where Hardy's pushing Ramanujan to actually prove his formula, not just state it, led to one of the great revolutions in the area called analytic number theory. Together, so first of all, this formula completely surprised all the experts. No one believed that it could possibly be true, but it's so pretty that Hardy immediately believed it. It has to be true. Who would have the imagination to come up with a formula like that? And also, when you plugged in values of n, it really worked. It really was, as n got bigger and bigger, the error was getting tinier and tinier, just numerically. And together, Hardy and Ramanujan actually proved this formula. And that proof was what led to what's called the circle method in analytic number theory, which today is the fundamental tool in analytic number theory. So Hardy's pushing Ramanujan to prove things actually led to a major technique in analytic number theory that transformed the area of number theory. You can't do a math lecture about Ramanujan without mentioning the taxi cab number. So Hardy tells a story. I remember once going to see Ramanujan when he was ill. I had written in taxi cab number 1729 and remarked to Ramanujan that seemed kind of a dull number. Ramanujan said, "No, it is a very interesting number. It is the smallest number expressible as the sum of 2 cubes in 2 different ways." These kinds of stories led Littlewood to say that to Ramanujan, every integer was his personal friend. You could name any integer, and he was intimately familiar with it. He had so many pages of mathematics that essentially every integer he had some experience with, some experience or other. And it was only recently that some mathematicians found the piece of paper from which he knew about 1729. So if you look there on the bottom there, 1729, he knew from one of his works that 1729 is 9 cubed plus 10 cubed, right? 9 cubed is 729, 10 cubed is 1,000, that adds up to 1729. Or it's 12 cubed plus 1 cubed, 12 cubed is 1728, plus 1 is 1729. And so this is an actual piece of paper from one of Ramanujan's lost notebooks that were found only in the last few years. And what was he doing there? This piece of paper has now led to all sorts of mathematical research. There's only found a couple. This happens with all of Ramanujan's works. You find a random piece of paper and suddenly revolutionizes a field. And so here's one such piece of paper. This has an interpretation in terms of cubic twists of elliptic curves, but in terms of popular mathematics, you've all heard of Fermat's last theorem, which says that x squared plus y squared equals z squared has solutions, like 3, 4, 5. But once you go to x cubed plus y cubed equals z cubed, or 3, the exponent's 3, you take them higher, then there are no solutions. So x cubed plus y cubed equals z cubed, that's the theorem of Fermat, that has no solutions in whole numbers. But what Ramanujan found is that, okay, that doesn't have solutions in whole numbers, but if you look here, he says that it's possible for a cubed plus b cubed to equal almost z cubed, just off by 1. And that's possible infinitely many times, and he gives infinitely many solutions to that, the smallest of which is 17. It comes up as 1729 on one side. And that's how he knew about that 1729 fact. But he had facts like this for basically any number you mentioned to him. So he proved that even though Fermat's last theorem can't have solutions, right? X cubed plus y cubed equals z cubed can't have solutions. They can have almost solutions, just different by 1, infinitely often. So Fermat's last theorem is very subtle. This kind of shows that it's very subtle, that you can't have exact equality, but it's very possible to have very close to equality. And so as I said, this work has now had implications for K3 surfaces and elliptic curves and a number of modern mathematical objects that just didn't exist at the time. And this is very typical of Ramanujan's work as well, that you wonder how he came up with those things when those mathematical objects just didn't exist at that time. He had his own way of coming up with them, and as decades go by, we understand what he meant. So, Ramanujan was a great anticipator of mathematics. He wrote down mathematical formulas that seemed quite random looking at the time. What is he talking about? And then as decades go by, those are exactly the things you need in order to solve some problem that came up decades later. And that's happened many, many times. I have a whole collection of such things, which I won't go through all of them. But 4 squares theorem of Lagrange, he had generalizations of that. So Lagrange's 4 squares theorem says that every whole number can be expressed as the sum of 4 square numbers. So when non-mathematicians first hear that, it's kind of surprising, right? Because square numbers get further and further apart. 1, 4, 9, 16, 25, they're getting further and further apart. And yet, no matter how big a number you take, it's always going to be the sum of 4 square numbers. Like 19 is 16 plus 1 plus 1 plus 1. No matter how big a number you take, it will always be the sum of 4 square numbers. That's Lagrange's 4 squares theorem. And Ramanujan took that as a starting point to completely change the field of what's called quadratic forms. And so I have a slide for this just because this was one of the starting points for my PhD thesis. And so for me, this is a very personal, it led to many things that I would go on to work on later on. Ramanujan's work on the 4 squares theorem. So I want to tell you one example that's really, really changed mathematics. And it's just one of the major themes of number theory nowadays. It really looked random at the time that he wrote it down. So one of the most important functions in number theory is called delta of q. It's called the modular form. And it's just defined as a simple, you take q times an infinite product. 1 minus q to the n, you multiply that over all n. Okay? Raised to the 24. Okay, and that's a very famous function called the modular form. And so what you can do is you can take that, what Ramanujan decided to do is you take that function and he multiplied it out. There are infinitely many terms, but you can multiply it out. And you get a power series, some tau of n, q to the n. Okay, so that's not surprising. But what Ramanujan decided to do is he decided to take those coefficients tau of n and view that as a function of n. And examine that. And no one ever thought that that itself could have properties. People knew that the modular form as a function of q had properties, but after multiplying it out and then looking at those coefficients as a function of n, that no one had ever done before. No one expected that it would have any properties that would be useful. Ramanujan decided to study the coefficients tau of n in the resulting power series as a function of the natural number n. So this is now called Ramanujan's tau function. And he made three remarkable conjectures. We call them conjectures because he just sort of wrote them down in his notebook. Nobody knows how he really came up with them, maybe just through lots of calculation. But they were kind of funny looking. So one was really nice looking. It says that tau of m times n is tau of m times tau of n. So for example, the sixth coefficient, he said, is going to be the product of the second coefficient and the third coefficient. Okay, so that's a very natural property. And that was proven by Mordell and Hecke. And those results of Mordell and Hecke later on have, again, transformed number theory. Led to the theory of Hecke operators, for example, on modular forms. Okay, so that was a very nice looking property. But then he had some funnier properties. Like if you take tau of a prime raised to r plus 1, he had a way of computing that in terms of smaller coefficients. And the formula, it was amazing that he could compute that, but it was kind of random looking. And again, that was also proved by Mordell and Hecke using the theory of Hecke operators. That was one of the reasons that Mordell and Hecke developed that theory. And now that theory has turned out to completely transform this entire area of mathematics. Okay, here's the real amazing conjecture that people thought was just completely random at the time. That if you take tau of any prime number, so in other words, if you take the prime number coefficient there, it's going to be less than or equal to 2p to the 11 over 2. And that people really thought was, well, why would you ever care about that property, and how did he come up with it? What is he talking about? And it wasn't until Delisle in 1978, so over half a century later, that was proved. And it was considered so important, that proof, that Delisle received the Fields Medal for the proof of this in 1978. And this property, now called the Ramanujan conjecture, holds in much greater generality than just for the tau function. It's an open question, and if it was known in general, not just for delta of q, but for general modular forms, it would solve many, many of the central problems in number theory. So this conjecture that Ramanujan made seemed completely random looking, is now become one of the central conjectures in number theory. And each time a case of it is proven, it has tremendous consequences for the area of number theory. So this was just to give you one example of how Ramanujan wrote down things, and then people thought it was completely random and foreign, and then decades later, it transformed mathematics. Okay, I'm going to end with just one last example, because this is another example of how decades later we understand the depth of what Ramanujan was doing. The very last letter that Ramanujan wrote to Hardy from his deathbed, some people refer to it as his deathbed letter, because it was the last one before he died. The last letter that Ramanujan wrote to Hardy, he said, "Dear Hardy, I'm extremely sorry for not writing you a single letter up to now." He's extremely ill on his bed, and he's sorry that he hasn't written a letter to Hardy for a little while. He says, "I discovered very interesting functions recently, which I call Mach theta functions." So I should tell you, theta functions are, for centuries, since the time of Jacobi and even earlier, theta functions have been some of the most important objects in mathematics, most important functions. And what Ramanujan says is that I've discovered very interesting functions which I call Mach theta functions, and they enter into mathematics as beautifully as the original theta functions. So he took these classical theta functions that people have studied for centuries, and he says, I've discovered an analog called Mach theta functions, and he claims, this unbelievable claim that theta functions completely transform mathematics. He's saying, I've discovered another kind of function that is just as important as those. And here are the pages from that letter where he's writing down these functions. And Hardy received this letter. Of course, he received the news of Ramanujan's death shortly thereafter. But he never saw, he thought, well, Ramanujan was sick. He probably, he thought these are very important functions, but they're kind of random looking. What could they possibly mean? They weren't really studied for the next 80 years. People looked at them a lot, and they said, yeah, it's clearly not the same thing as theta functions, and they're kind of weird formulas, as was the case with many of Ramanujan's things that we're still finding. So these Mach theta functions that he claimed were just as important as ordinary theta functions were a complete mystery until 2002, so 80 years later. PhD thesis is Wager's, who showed that Ramanujan had actually discovered what are now called mass forms, which are another very important kind of modular form, very important kind of function. So he had discovered these mass forms, but in particular, these Mach theta functions that he defined are a special case of what are now called Mach modular forms in honor of Ramanujan calling them Mach theta functions. And since 2002, this has caused a revolution in this area of mass forms. And they've been studied now heavily for 15 years. So there was nothing going on for 80 years, and then suddenly we realized what some of these expressions that Ramanujan wrote mean. And that caused a revolution, and now so many works are being published every week about this subject. So this is something very recent. Just in the last couple of years, it's completely gone to new heights, and suddenly it's being applied to physics. So it turns out that in studying the entropy of black holes, there were needed some functions to describe the behavior of these black holes in physics and in string theory. And now that these functions of Ramanujan were understood, it was realized that these are exactly the functions that were needed to understand black holes. And so these Mach modular forms are suddenly living up to these expectations. They've now moved to neighboring subjects, not just in mathematics, they've become very important, but also in physics. And so here's one of the end cards of the movie. A century later, these formulas are being used to understand the behavior of black holes. That last letter that he wrote on his deathbed is now being used to understand the behavior of black holes. So this is one of the last end cards in the movie that show. So this is an actual scene from the movie, and in particular this. So I just want to say thanks so much for your support for coming here. I wanted to show you some of the clips of the movie. I understand that, so the movie will be coming out in England on April 8th, but as usually happens in Paris, it will come in September. It takes a little while. For some reason, Hollywood movies start going through England first, and then they work their way around the world, and Paris seems to be one of the later places that Hollywood movies open. I'm not really sure why. But I hope that we'll have your support on this movie, that people will go and watch and spread the word. Because if a movie, first of all, it'll spread the word about mathematics in a way where mathematics is, I'm very grateful to the director and writer that he actually made sure to have mathematics in the movie as a human element, accurately. The life story is accurate. So everything in the movie was tried to, every effort was made to make everything as accurate as possible, both in the life story and in the mathematics. And if this kind of movie does well, then we can hope for more such movies in the future. So support for this kind of movie is really important from that point of view, to get the word of science out there to the public in a real, true, human way. And that's what we really tried to do with this movie. So thank you so much for your attention, and happy to take questions. Maybe I just end by showing you, this trailer is available online just now, but I'll end by just showing you just a 2-minute trailer so you can see what it's.
What do you see?
Sand.
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Intervals, infinite series.
Like from an Indian clerk, ill-educated in Madras, I would very highly value any advice you give me.
Letter for you. Postmarked England.
Yours truly, S. Ramanujan.
What does the S stand for?
Can you ask himself?
You intend to invite him here. Don't be intimidated. Great knowledge comes from the humblest of origins.
For the good of everybody, you should attend some lectures.
I'm here to publish, but that only contain a small sampling of my discoveries.
This will take a lifetime.
Maybe two.
We need proofs of your work.
But they are right, sir.
I haven't completed that proof. How do you know?
I just do.
You don't pull a stunt like that in my class.
How do you know that theorem?
It came to me. These steps you want, I do not know how to do.
Where are you going? This is our home.
Don't you know what I have given up to be here? I have nothing. You wanted to know how I get my ideas. Go on, speak to me.
There are no proofs. We're just supposed to take him at his word? No, you're to take him at mine. Why do you do it?
Because I have to.
There are no proofs that can determine the outcome of matters of the heart. We are merely explorers of infinity in the pursuit of absolute perfection.
I owe you so much.
It's I who owe you.
Thank you so much.
Bonsoir à tous, donc merci d'être aussi nombreux. Je voudrais d'abord vous remercier au nom du CNRS, remercier l'Université Pierre-Marie Curie pour son hospitalité, la délégation permanente de Rennes de l'UNESCO, son soutien, son initiative, les laboratoires, le STA, le LPAMAN, l'IFJPRG, le LJLM, qui nous ont beaucoup aidés. Madame Kékou, Marine, Christine et tous les autres qui ont donné tant de temps. Et bien sûr, Ramanujan, pour son magnifique exposé.
Thank you, Manjul, for that fantastic start to the International Conference on the Zero. My grateful thanks as well to the University of Pierre and Marie Curie for collaborating with us on this event. Special thanks to David Zer0 for being at the center of this collaboration. And of course, a huge thanks to the audience for being present in such encouraging numbers. It is a pleasure to be amidst young, bright and inquiring minds who will inherit this brave new world of ours. But there are no endings, only beginnings. Tomorrow at UNESCO, this conference will continue with a further 5 sessions. And for those of you who have not had enough of Manjul's brilliance, he will be speaking again tomorrow at UNESCO on 2 totally different subjects. The one on music in Indian mathematics from 2 p.m. to 3 p.m., highlighting what we always suspected, the probable link, or rather should I say the potential link, between mathematics and music. Is this correct? Surely Manjul will have all the answers tomorrow. And a little later, between 4 to 5 p.m., he will speak on the legacies of the ancient Indian mathematicians and their incredible contribution to the domain of mathematics. For this session, the high-level segment of the conference, we will be specially honored to have in our midst Professor Laurent Laforgue of the Institut des Hautes Études Scientifiques. All of you know of him, and he will speak on the importance of simplicity in mathematics. Fascinating indeed. Needless to say, both our distinguished Fields medalists will speak in the presence of the Director General UNESCO, Ms. Irina Bokova, and the Minister of Education of India, Ms. Smriti Irani. Honestly, things do not get any better. So in thanking Zer0 once again, and in saying how pleased I am to be with this wonderful audience, I very much look forward to the pleasure of welcoming you tomorrow to UNESCO. Thank you very much. Yes, I can see your question. So Deepak is going to pose the first question.
Normally when we hear about the geniuses in music, they have such a good notion of notes which are imparted by a ustad or someone, and they play with it to bring out some melody. How do a mathematician sees the number, you want to play with them and bring out some harmony? How does it work out in your brain?
Yes, it's a good question, because Ramanujan is a different kind of example where he didn't really have a teacher, but he did have one source of inspiration, which was his book with 6,000 theorems, in which he sprung and played with and discovered many, many more things. So a source of inspiration is really important. He was lucky, even though he didn't have teachers, he was lucky to have a library close by where he could look up things. And he did have that one book to take inspiration from, and that was very important. So having that seed to start with, from which you can then play and find your own path, is very important. But that's why I say it's very important for all the students to have, all kids in the world to have an opportunity for education, to get that seed of inspiration from which they can jump into great things. Yeah.
I never have heard anyone answer this question. In all of Ramanujan's results that he wrote down, was he ever wrong?
He did, yeah. So actually, he did have some really, really interesting mistakes, and some of his mistakes actually have been great sources of inspiration for mathematicians. So there are some instances in his work where he didn't know that he hadn't had education about the Riemann hypothesis, and so he was proving subtleties when he didn't know about the Riemann hypothesis. When people inserted the Riemann hypothesis, it led to a big breakthrough. So sometimes he had these little holes in his knowledge that led to subtle mistakes that were often deep. So one of the things that I worked on as a PhD thesis was he had a generalization of Lagrange's four squares theorem. He had 55 generalizations, of which one was wrong. And that one mistake was what led to my PhD thesis. That mistake was so interesting. And it really got to the heart of a matter that he just happened not to know about. So even his mistakes were often really interesting, great mistakes that also led to revolutions in the area that those mistakes were in. Yeah, but he did have a few mistakes. But the vast majority of his notebooks, people have been proving the statements in the notebooks for years now. And the vast majority of the statements that he made were correct. And in the few instances that there were mistakes, almost inevitably they were really interesting mistakes. If you find a mistake, it's even sometimes even more, mathematicians have jumped on it even more because it's led to just great things. But the vast majority of these things have so far been true. Of course, there are many more things that have not yet been proven or really understood, and so there's still, we have some way to go with that. But the vast majority of things that he wrote down have now been proven to be true.
So it actually speaks to Hardy's merit. So Hardy could see that there was a mistake in the way.
Oh yeah, right. I mean, one of the things.
It's dramatized here.
Right.
Yes. Here's it's dramatized. He claims to have an exact formula for the number of prime numbers, and Littlewood says it will take a lot. In fact, it took Hardy very little time to. Well, he could realize he knew that the formula was wrong, and he could tell why the Ramanujan was.
And he still didn't just throw it out.
Exactly.
Because he knew, right. Yeah. So and that mistake is talked about in the movie. I didn't show that clip, but that is talked about later in the movie. And that is one of the tensions that between Hardy and Ramanujan, and one of the things that does convince Ramanujan to listen to Hardy and jump into doing proofs. Any other questions?
Is there still a big percentage of statements that are not proved?
Yeah, so the question is, are there still many statements of Ramanujan that are not proved? So in one sense they're not, in that most of Ramanujan's statements have now been verified, in the sense that proof has been given, but the proof has really no understanding. So for example, that example I gave of Ramanujan's deathbed letter, where the PhD thesis in 2002, a lot of Ramanujan's statements were verified, But it's not until now that we're really understanding the depth of what Ramanujan meant and what. So there's a difference sometimes between a proof that just verifies a statement and a proof that really sheds light on the depth of what's really going on there. And so I'd say a lot of Ramanujan's work has been understood, but most has not. But most has been verified. But most, what the depth is, where he came up with it from, and why, and what the beauty is in there. A lot of it still remains to be understood, and lots and lots of mathematicians still work on that. And every day there are new things that come out where suddenly it's not just verified, but a statement of Ramanujan is actually understood, and it's applied somewhere and leads to many deep things and a new area of mathematics that it often spawns.
I have found an interesting point in the book that you mentioned, The Man with the Infinity. I think it's interesting that you emphasize in your talk in the movie that Hardy was an advocate of rigorous proof in math. And this was new in England. Apparently Hardy is the first who had imported the rigor of German and French mathematics into England at that time. And maybe 20 or 30 years before, the British mathematician would have insisted less on the need for rigorous proofs.
Yeah, that's very true. It's really interesting that match between Hardy and Ramanujan happened, because Ramanujan was the epitome of not proving anything rigorously and just writing more and more statements quickly. And Hardy, on the other hand, was one of the people who really insisted on rigor, and one of the rare ones in England who insisted on that much rigor. And the fact that those two came together in this unlikely friendship is in large part what drives the movie. That they come from. There are lots of other tensions between them. Ramanujan was very religious. He said that his mathematical findings came as visions from his hometown goddess Namagiri, whereas Hardy was a complete atheist. And so that was one tension between them. The fact that he was coming from India, from a traditional family. Hardy was completely the opposite. He was English, one of the conquered, one of the members of a citizen of the country that had conquered India. So, and Ramanujan was was a citizen of colonial India. And then rigor versus non-rigor. There's so many tensions between them. Hardy also was completely married to his mathematics. He had no family life. It was all about mathematics for him, whereas for Ramanujan, it was actually, his family life was extremely important, and that was something that Hardy could not understand. That why he was missing his family being in England when he could be doing mathematics with them. And so there are all these kinds of tensions that are brought out in the movie. They're really unlikely friendship that led to one of the greatest collaborations of all time, and that's what makes it such a great story.
My understanding is that he was especially attached to his mother. In fact, something that changed the movie, from what I see, is that
who's he?
He was especially attached to his mother.
Who? Oh yeah.
But it's not sure that he changed the movie. He said, well, the rich mother is actually the cow guy. So she was
his wife is shown as actually, there's some age, for example, Hardy was a lot younger than he's portrayed in the movie, but as far as the portrayal of the friendship goes, it doesn't really affect that too much. One of the things that's shown in the movie is that Ramanujan and his wife Janaki, actually they exchanged letters throughout his time when he was in England. But his mother, Ramanujan's mother, didn't want Ramanujan and his wife to move to England. And so she actually hid the letters that they wrote to each other. And that's another big source of tension and stress that Ramanujan had, that his wife wasn't writing back. She was, actually, but their letters were being hidden. And that's another big source of tension and difficulties that Ramanujan had to face when he was in England.
Not very nice.
Yeah, that was tough. But she wanted, Ramanujan's mother wanted to make sure that Ramanujan returned back to India. Of course, she regretted what happened as a result of this later on, obviously.
D'autres questions, commentaires? Oui.
How long did it impact in India, mathematician in India? How long did it take that it impacted the people in India, the mathematician in India?
How long did it take for his work to pack
Yes.
students in India? Well, in some sense, it's still happening. It's taken a long time. Ramanujan, surprisingly, is not a household name in India. I actually gave a lecture about Ramanujan in a city called Jaipur 3 days ago. I asked the audience, who's heard of Ramanujan before? And maybe a third of the people raised their hand. A lot of them, mathematics students. Hopefully this movie will have an effect. But the number of people that should, the amount of talent for mathematics in India is huge, but somehow in the education system it hasn't, Ramanujan hasn't made his way through into the education system. A lot of the textbooks are still from colonial times, and they haven't changed. And so hopefully this movie will help raise awareness, and eventually textbooks will be changed, and more people will learn about Ramanujan's work in India too. Of course, the experts all know about him, the professional mathematicians, but even college students who are math majors often have not heard of Ramanujan. It is, yeah, I was very surprised as well. No, Tamil Nadu, of course, a much bigger percentage of people know about Ramanujan. I'd even say most, but in the rest of India, yeah, it's amazing how little he's known in India. Almost, you think he's known more outside India than in India sometimes. But hopefully that'll change soon. The movie comes out in India on April 29th, so it's fairly soon. Hopefully that'll help bring the word of mathematics to the public in India as well. And a hometown hero for India. He should be.
D'autres questions?